Hi, in this video, we want to take a look at goodness of fit measures. All right, so our idea here is that we have some form of mathematical model for the data that we have, and we want to see, does it look like we have a good fit? So we have goodness of fit measures. All right, so there's going to be two approaches to this. There's going to be measurements of goodness of fit, and there's going to be hypothesis tests for evaluating if what we have looks like it's going with the hypothesized distribution. All right, so goodness of fit tests and measures are used in statistics to compare observed data with modeled outcomes or theoretical distributions. These tests are used to validate whether the data significantly deviates from the expected model. All right, so goodness of fit measures provide numerical values indicating how well a statistical model fits the observed data. Unlike the test, these measures often do not come with probabilistic interpretation, but can be used for comparing different models. All right, so I'm going to go over the three types that we're going to talk about first, and then we'll go a little bit deeper into each of the three. So we're going to talk about two different distribution fits. I'm going to say fits of distributions for continuous distributions, and then we'll have categorical fits for distributions also. And then the one in the middle that we'll talk about is regression fits. So I have a regression model, and I want to evaluate, do I have a good fit for my data? All right, so often we want to test whether a random variable follows a certain theoretical distribution. And when I say random variable, that's going to be our observed data. For instance, we may want to check to see if a set of observations follow maybe a normal or an exponential or Poisson distribution. All right, so what we're going to do, the first one we're going to look at is Kolmogorov-Smirnov's test. And let's say that f sub 0 is the cumulative distribution function of our hypothesized assumed theoretical distribution. And let's say f sub n is the empirical distribution that we observe. All right, so what we're going to do is we're going to take the cumulative distribution function we have in theory, the cumulative distribution function that we have from data, and then we're going to look at the supremum of the difference between the two functions. All right, now it's a supremum, not a maximum. There's a small difference between them, but we're really the big idea here is I take the two cumulative distribution functions, one's theoretical, one's empirical, and I look at the biggest difference between them. And so D is going to be the maximum difference or the supremum over all possible points of X. The smaller the value of D, the closer the observed distribution is to our assumed theoretical distribution. Now, the next one I want to talk about, or next category, is regression analysis. Now, there are tons and tons of measurements, but first I'm going to kick it off with the most well-known one that we know and love, R squared. So in regression analysis, the objective is to model the relationship between a dependent variable, the outcome, and one or more independent variables, our predictors. In a goodness of fit context, usually this refers to how well the model predicts the dependent variable given the values of the independent values. A commonly used measure of goodness of fit in regression is the coefficient of determination R squared. Now, this one has some problems with overfitting, but it's by far the most well understood of all of the goodness of fit ones, so I'm putting it here in the video. And so here we have our sum of squares for residuals, divided by sum of squares total, and then 1 minus that, and that will be our R squared. If R squared is closer to 1, then that's an indication of a better fit. Now, if R squared is closer to 0, that's a weaker fit. Now, something to be mindful of, if I have overfitting, R squared can look bigger than it should in reality. Now, for categorical data, we want to see if the observed frequencies of our categories match expected frequencies. For instance, we might want to check to see if some dice are fair, or so we can look at how frequently each face appears while we're rolling dice. So let's say that O sub I is the observed frequency, E is the expected frequency, off of the ith category. I goes over all our possible levels. And a common goodness of fit is going to be the chi-squared statistic, which will follow a chi-squared distribution, by the way. Observed minus expected, square it, divide by expected, and then add that up all over the different levels that we have for our categorical data. Under the null hypothesis that the observed and the expected frequencies are equals, this statistics follows a chi-square distribution with k minus 1 degrees of freedom. K is the number of levels that we have for our categorical data. The larger the chi-squared, the greater the difference between our observed and expected frequencies. So a large chi-squared indicates a poor fit of the data to the assumed distribution. All right, so now let's go in a little bit deeper onto the distributions, goodness of fits. All right, so first we're going to talk about the measures, then we'll talk about the hypothesis test. So we have AIC, Akaike's information criterion. And so here we have 2 minus the number of 2 times the number of parameters we have minus 2 times the log of the likelihood measurement. All right, and so here what's going on is I want a lesser value. A lesser value means a better fit. And the parameter aspect is we're trying to balance that overfitting aspect I talked about previously, where if I have a situation where I have lots and lots of parameters, things will just end up fitting just because I have more flexibility, not because it's a good model. And AIC and BIC try to balance out that aspect. Now, the Bayesian information criterion, BIC, is very similar to AIC, but we multiply by the log of our number of observations instead of 2 in AIC. So here we put a stiffer penalty on the number of penalties. So BIC will prefer to have fewer parameters more than AIC will prefer to have fewer parameters. There's also a kernelized Stein discrepancy. I'm not going to talk about that too deeply, but it is one. If you don't feel satisfied with the other measures, you could use this one. Now, when we talk about these goodness of fit measures, these are for when I have the same data set and I have multiple models I want to compare. Same data, multiple models, which one's the best one to work with? And different measures can lead to different conclusions. Now, goodness of fit tests, first one we're going to talk about is the Kolmogorov-Smirnov test. And so here, I take my theoretical distribution, I take my empirical distribution, take their cumulative distribution functions, take the difference, find the largest value of the difference. And it'll be a supremum. Most of the time it'll be a max, but supremum is close enough. And so then we're going to use this to run a hypothesis test to see, hey, does it look like we have 2 different distributions? And so our null hypothesis will be that our observed data follows the theoretical distribution. Our alternative hypothesis is that our observed data does not follow the theoretical distribution. Now, the Anderson-Darling test, this is a non-parametric test that can be used to compare a sample of data with a given probability distribution. It places more weight on the tails than a Kolmogorov-Smirnov test. And here is the test statistic. It's kind of long, a lot of stuff going but really just think of it as if I feel like Kolmogorov-Smirnov test is not really doing the job. The reason why a lot of statisticians don't like the KS test is because it breaks it down to one number, and that one number, it's too much of a simplification. And so sometimes statisticians don't like to use the KS test, and so we can move to Anderson-Darling. Now, the chi-square test, another approach that we can do and we're still talking about numerical or continuous distributions, what we can do on this one is if I was to bin the intervals of my data, I could go ahead and get observed and expected counts. Once I have those counts, I can run my chi-squared test. And so here we'll use the chi-squared distribution with k-1's degrees of freedom to make a conclusion of whether our data follows the given distribution. Now, this isn't a great choice, but this is one that I've had an easier time convincing stakeholders with. And so I've used this in the past when I had a stakeholder who was comfortable with, let's say, like a year or maybe a semester of introductory graduate level statistics or a year of undergraduate introductory statistics. And so they knew a few of these words here and there, and they were comfortable with chi-squared tests, but they didn't know the other tests because it wasn't part of their course. And so since they were okay with the chi-squared test, for that client, I always ran it and I used it in this situation. That way, they were more receptive to my work. Now, the Shapiro-Wilk test, this one is for the normal distribution. And this one, most of the time when I have very large data, it will practically automatically reject the null hypothesis in favor of the alternative. The null hypothesis is our data follows a normal distribution. The alternative is our data is not from a normal distribution. I made a typo here and forgot to put in what I intended to put in there, but I'll fix that for class. Now, the Hosmer limit show test, this is specifically for logistic regression. And so with logistic regression, we can run this to check to see if we have a goodness of fit. Now, for the regression goodness of fit, the first one that we want to talk about is the coefficient of determination, that is R squared. And so this tries to give a representation of the proportion of variance accounted for by the independent variables. All right, so it ranges between 0 and 1. Closer to 1 means that we have a better fit, and 0 means we have a lesser fit. But remember, we always have to worry about the possibility of overfitting with this one. Now, the next one is the lack of fit sum of squares. Lack of fit sum of squares is a measure of how well a regression model represents the data being modeled. In other words, it measures the gap between the observed values and the values predicted by the model. A smaller lack of fit sum of squares indicates a better fit. If Yij are the observed data and Yij hat are the predicted values, and Yi bar is the mean of the values for that combination of predictor variables, then this is our lack of fit sum of squares. Actually, this should be that bar. I made a mistake. So the lack of fit, we should have the bar in here, by the way. Now, Mallow's CP criterion is a measure that assesses the fit of a regression model based on the number of predictors in the model. The goal of the CP criteria is to find a model with a CP value close to the number of predictors plus a constant. And so here I take my sum of squares error with P predictors. S squared is the estimated variance of the error term. N is the sample size, and 2P is P is the number of predictors. Now we can also look at our prediction error. That's just observed minus model values, square it, added up. And we can also use reduce chi-squared. So reduce chi-squared, it's just like chi-squared we talked about previously, but we're going to divide by the degrees of freedom. And this is to normalize the situation because there's a connection between the expected value of chi-squared being equal to the degrees of freedom. Now, for categorical goodness of fit, we're going to have our chi-square test. So here we're taking the chi-square statistic we talked about previously, and we're going to apply it to the hypothesized probability distribution of chi-squared with k-1 degrees of freedom. We can also do a binomial test or a proportion test. Here I'm using a proportion test using the normal approximation. And so this will work for 2 category data. There's also the g-test, which is the likelihood ratio test. This is another test for comparing observed and expected frequency. It is based on the likelihood ratio, which is a measure of how likely observed data is under the hypothesized distribution. All right, so now let's run through examples using R. And so the Kolmogorov-Smirnov test is just a ks.test. And here our null hypothesis is that we have our data coming from the hypothesized distribution. Our alternative hypothesis is our data is not from the given distribution. And so something we have to do, we have to indicate what is our distribution to be working with. And we get our p-value. So remember that under our null hypothesis, we're prone to failing to reject the null hypothesis. With this setup, we would have to have extremely different data for us to conclude we have 2 different distributions. Now, Shapiro-Wilk, this is very, very sensitive to large sample size. If I have a large enough sample size, it will almost always reject the null hypothesis. And so here, my null hypothesis is our data is from a normal distribution. The alternative is that it's not from a normal distribution. So we conclude that it's not from, or sorry, we conclude that it is from a normal distribution. And we use a chi-square test. Here instead, so I could do this by partitioning a continuous variable first, then running the chi-square distribution. Now for Anderson-Darling, and this one isn't used nearly as much as the others, but it's definitely a good test to use. Here we're going to use the NOR test package, and it's the ad.test function. Now for regression goodness of fit, we're going to use R squared from the summary function to get our R squared value off of our linear model. To get Mallow CP criterion, what we're going to do is we're going to use the ordinary least squares RR package, ordinary least squares Mallow CP, and then this function will spit out the value for me. For prediction error, what I'm going to do is I'm going to take my residuals, and either I'm going to take the absolute value and add them up, or I'm going to square them and add them up, depending on what I'm working on. And then for reduced chi-squared, I just take that chi-squared statistic that I'm going to get, which will be my residuals squared, add them up, divide by degrees of freedom. And so here we want to see a value close to 1. This is a bit off from 1. All right, so now the categorical goodness of fit with R, I can use Pearson's chi-squared. So here that's just chi-squared.test. This one, I have used this function a lot at work. For the binomial test, we have 2 options. We have binom.test and prop.test. Binom.test will use the actual binomial distribution exactly, while prop.test will use the normal approximation of the binomial distribution. And so I prefer the binom.test because I know it's more precise, but it's really not much of a difference. If you give me either one, I'm going to accept it as correct. I know statisticians that until I told them didn't even know that binom.test even existed. They've just been doing prop.test for like 20 years. Now, g-test, we have to create a special function for this and crunch this out. So conclusion, goodness of fit measures in statistics provide a quantitative way to measure how well a statistical model fits a given set of data. These methods come in various forms and are applicable to different types of data and situations. For continuous data, we often assess the goodness of fit by checking the difference between observed and predicted values. As in the case of R squared and the sum of squared residuals in regression analysis, we might also compare the empirical distribution of a data set with a theoretical one using methods such as KS or Anderson-Darling test. For categorical data, we may be interested in comparing observed frequencies of categories with expected ones. And so we'll use things like Pearson's chi-square test, g-test, or binomial test for this. All right. So here's the homework problems. That's all I've got for you. Life is short. Do math.